This will be our third and final video on the integral test for infinite series. So in this lesson we're going to look at examples of the bounds that we derived in the first two lessons, and we're going to use them to prove the convergence or divergence of two different series. So as in the first two lessons, the series that we study have this form shown here. It's a sum from n equals 1 to infinity of f of n, and where this f is a positive decreasing function of x. So let's go right ahead to the first example. In this example, we're going to use the bound from our video part 1 on the integral test. And in this example, we're going to look at the series defined by f of x equals 1 over x squared. So the series is the sum from 1 to infinity, 1 over n squared. And if you remember from the first video, this series does converge, and it's actually equal to pi squared over 6. And for later comparison, I'll just note that this is about 1.64 ... And remember that this result was a famous math problem called the Basel problem. So now we're going to use the integral test to prove that this series converges. And to do it, we're going to use this bound from our part 1 lesson, that this series is less than or equal to f of 1 plus the integral from 1 to infinity of f of x. Now in our case, f of 1 is just equal to 1, so we just have to evaluate the integral. And let's go ahead and do that here. We have the integral of 1 over x squared. It's equal to the integral from 1 to infinity of the derivative of minus 1 over x. So we have minus 1 over x, and we have to take its value at infinity and subtract the value at 1. And if you do this, you'll get 0 minus negative 1, which is equal to 1. So when we put this all together now, we find this bound. Sum from 1 to infinity, 1 over n squared, is less than or equal to 1 from the f of 1, plus 1 from this integral, which is equal to 2. And you can see that 2 is greater than or equal to the exact value, 1.64 ... So the integral test worked for us, and it shows us that this series converges. So now we're going to move on to our second example. So in the second example, we'll use the integral test to prove that a series diverges. And in this example, we're going to use the bound that we derived in our part 2 video on the integral test. And the function that we'll look at is f of x equals 1 over x. So we have this series, sum from 1 to infinity of 1 over n, and I'll just mention that this is called the harmonic series. So we're going to prove that this series diverges, and to do it we're going to use this lower bound on the partial sums. So we're going to look at the partial sum from 1 to capital N of f of n. And you may remember from our first video that we derived, or the second video, that we derived this inequality. So the partial sum is greater than or equal to the integral from 1 to capital N plus 1 of f of x. So now we have to evaluate that integral. And what is it? So we have the integral of 1 over x from 1 to n plus 1. And this is equal to the integral of the derivative of log of x. So we have log of x, and we have to take its value at n plus 1 and subtract the value at 1, and it just gives us log of capital N plus 1. And so now, the key point here is that if we take the limit as capital N goes to infinity of log of n plus 1, it blows up and we get infinity. So we learn from this that as we take capital N to infinity and we include more and more terms into the series, that the series actually diverges. So this harmonic series, sum from 1 to infinity of 1 over n, diverges. And we can prove it using the integral test. So that's the end of this lesson.